Okay, so today we will continue our discussion on chapter 5 on energy storage. On the previous class, we have discussed about capacitor, and today we will continue our discussion on inductor, another components in electronics and electrics that able to do the job of storing energy. Okay, so at the end of the class, I'm expecting you guys to be able to identify the type of energy storage device and then explain the working principle of inductor actually. And it's supposed to be inductor. And then finally able to calculate how inductors in the circuitry works based on their connectivity. So these are the things that we will learn today, and hopefully you will guys will be able to grasp the ideas what inductor is all about. So what does how does it look like? It's look like this. Okay, so inductor is like a coils. It's actually a coil, and it can be in the form circular like this, or in the form of square like this. Okay? So as you can see here, all the inductors are having a circular coils. In the middle of it, we have a core. We call it a core. It comes in various size, but the inductor mainly have a big size, and that's why. But it has the smallest one is also. You can see here a very small footprint, but still considered big when compared to other SMT components. So the symbols, you can use the symbols. The generic symbol is just a basic coin like this, and when you're seeing this, then you can differentiate between the symbol of inductor and resistor, which is slightly different. So some people have put it inside the iron core like this to show that the inductors has an iron core. But does it have polarity like battery? The answer is no, actually. So inductor don't have any polarity, so you can put it in the both ways. There is no problem. So if you put it upside down, or because it has no polarity at all. Okay. So what the structure of inductor is built by a few parameters. The first parameters is the cross-sectional area, E. In this area, it's determined the area for the flux to develop inside. And then you have the length of inductors. So the length of inductors is also play a role here. And then you have another one is turns. And turns, how many turns you have inside the inductors will determine the value of your inductance. Okay. And then we have also the current that flowing through and the voltage that applied across the inductor. That also will play a big role in determining the value of the magnetic flux that produced in the inductor. So you have inner core material. The material also play a part. It can be as a air, that's like normal air, or it can be just metal to improve the value of inductance. So there are so many these are the parameters that set the value of inductors in the electric circuits. Okay. So how we measure it, the unit is what we call as a Henry. So it's always at the range of milli or microhenry, slightly bigger when compared to capacitor. Capacitor is always in micro to nano picofarad, nano and picofarad, but inductor is slightly bigger from micro to milli Henry. So those are the range that typically used in the electric circuits. So it depends on the structure of the inductors. And then in order to calculate the inductance for solenoid wounds inductor, calculation is fairly simple. You have the L, the inductance value is equal to N squared times mu A divided by L, or length. So N is the amount of number of turns, mu is the material property of the core materials, and then the A is the area, the cross-sectional area of the coil, and then finally you have the divided by the length, because the length will determine how big the inductor will be. So mu is the permeability of the core, and the L is the length, and the A is the cross-sectional area. So actually how this inductor works, we can say that inductors works in the more or less the same like capacitors. Okay, so at the very beginning of the circuit, when you have a voltage source, let's say you put a voltage source inside, and then you put a switch in open state, and you connect it to one inductor. In this situation, because the is not completed, since the circuitry is not complete, so there is no current will flow across the circuit. Now, here what we call is this uncharged state, or the circuit is open, so there is no current flow, there is no magnetic field produced by the solenoid or inductors. Okay, next. So as we close the circuit or to switch on the circuit, okay, as we switch on the circuit, and then as the circuit is closed, then the current will start flowing in the circuit, and the current will flow across the coil, line by line, turn by turns, and then this flow of current will produce or induce magnetic field. Okay, so in the magnetic field, so that's why normally the inductors is in the form of a solenoid structure like this, and then you have a very strong magnetic field will be produced across the inductors, and then which limit the flow or produce a high resistance. So a magnetic field is induced, and then will limit the flow of current in the form of high resistance. After a brief moment, the magnetic field will be at the peak. So we have reached the maximum magnetic field can be produced by that inductors. So in this case, okay, so the resistance will drop because the current that flowing across inductor is not being used anymore as a magnetic field. So you can say that the resistance will be dropped, and then it will be shorted the inductors. Okay. So you can see the example of this kind of action. I can give you a fairly easy to understand in the sense of what we have in the coil ataupun relay coil. This is what we call as a relay coil, di mana where this relay coil is being used until today, even though it is very first switching elements before semiconductor switch take part. So all devices are derived by, all logic circuit are derived by this coil, relay coil, because it can give you on and off state. Okay, so here you have a inductor in the form of solenoid over here. So we can see that when you have a solenoid like this, when you energize the short circuit or give voltage across the coil terminal, the current will flow in this electromagnetic in this solenoid, and electromagnetic field will be produced. This electromagnetic field which produced inside the core will give a very strong attraction to the armature arm here. So as you can see, when this armature arm is being attracted, so the switch will from open to close contact. You see. Okay. So here you can see the state has been changed. If initially without any voltage across the terminal, coil terminal, you will have the armature that open or touching the normally close contact area here because of this spring. So this, without any magnetic field, this spring will pull this armature to the so that this common contact will touch at this point. Okay. So this is the area that will give you off state. So when you apply voltage here, positive and negative, current will start flowing inside the coil, right? So magnetic field will produce and push, or not push, pull the armature and make contact between this region. So now the signal, let's say the common terminal signal. So you have, let's say you have a signal from here. Now it can transfer to this part. Okay, so that's how we use inductance effect in the coil, so that we able to really make a contact and control the contact from the very small voltage by the coil terminals. Okay, so that's why until now electromagnetic coil or relay, electromagnetic relay is still relevant because of the ability to handle high voltage, because you can design a big armature structure that able to handle high voltage and can be controlled with a very small electromagnetic current. That's the advantage. So in summary, inductor allows current to flow slowly and increase in a brief moment before it acts like a closed switch or shorted, which is the maximum current flow. And when this happens, this inductor is said to be in the full charge. So same, when you are at that point, when it's a full charge, then there will be no more current will flow. So next, how it, let's see when we connect this full charge inductors into the load. Okay. So replacing battery with the load, and the electromagnetic field in the inductors will collapse, which is create potential, and the current will start flowing. So current will start flowing back to the load when you replace the battery just now into a load. Okay, so there is a different potential, because when it's fully charged at this point, current will not flowing anymore, because you have a same potential here and here. Dah sama dah potential again. So if this is 5 volt, this is also a 5 volt potential. And then when you replace the voltage source into the current source, into the load or like a resistor, then here is actually initially is 0, right? And then you have a voltage here, and this will initiate the movement of current to. Okay. So as the electromagnetic field collapse, as you can see here, you can see here again, I tried to show that it has a very strong magnetic field and the current still start flowing. And then as the magnetic field is starting to diminish, and you can see that the current will, the magnetic field is smaller, and the current also become weaker or smaller. because of the loss, so no more current will, and finally current will start flowing until it stops. So here you have a fully discharged state of a inductor. So that's how the inductor, the charging and the discharging inductors phase of working, where the electricity or the current were converted into a magnetic field form, and this will act like a charge storage, and then when there is no more charge or there is no more power source, this charge can turn into or have a certain potential value and make current flow nicely inside the load circuit. So a charge inductor acts like a current source for a brief moment before all the electromagnetic field collapse. Okay, so it becomes like a current source. Okay. Okay, any questions so far? I would like to see if you have any question, or shall I proceed? If there is no question, then we can proceed with the slide. Let's see first. Checking the chat. Okay, lecture note saya dah lecture note saya dah post pada dalam grup mana dalam grup ni? Classroom saya. Okay. So capacitor, after this I will put the inductor. So the lecture notes is already inside the Google Classroom. For the previous one, just let me know if there is no other slide yang I miss out. Okay. So next. So voltage exists across an inductor as long as there is a change in current. Okay. So a change in current, once the current remains constant, once the current remains constant or fully charged, in this situation, the voltage will be zero. That's the situation when you have current flow through electromagnetic coil or as an inductor. Since when you start flowing to the inductors, and this action will create electromagnetic field across the solenoid, and from here you can see that it will be reach a maximum magnetic field that can be produced by the solenoid or inductors. Then you will have a current that remains constant, and then from here you will have a voltage at 0 point. So in order to determine the voltage across inductor, we can say that V is equal L times di over dt, which means the integration of current with respect to the time. So because like capacitor, inductors, they are changing over the time. It's not like resistor. Resistor, they are not changing over the time. They are maintain the behavior as T is equal 0, T is equal 1, and so on. But in capacitor or inductor, they will always changing or depending on the times. So if inductor, the voltage will be changed over the voltage value can be determined by the change of currents over the time. So V is equal L di over dt. So the current flowing across a capacitor is dependent on the voltage at the given time and also the initial condition, hence memory effect. So So I here we can calculate since I is equal 1 over L kamian terhadap T, T0, Vt dt plus I during T equal at T0 lah. Okay. Initially, this is what we call as an initial condition, the current at T0, and then the plus the current that changes over during the T0 to T1 or T2. So the current flowing across capacitor is dependent on the voltage at the given time and is also the initial condition. Hence, we have a memory effect in this situation. An inductor, the ideal inductor doesn't dissipate energy, which means you convert all the currents into work. So W is equal to half Li squared. So W is equal half Li squared. So let's go through the first example on how to calculate or how to determine the inductor's behavior. Can you try first? So find the current through 5 Henry of inductor if the voltage across is Vt equal 30 times T squared when T is bigger than 0. Right? So maksudnya T sama 1. So the behavior of voltage will be 30 times T squared. So below 0, the voltage is 0. So also find the energy stored within 0 to T5 second, which is we assume that I0 is equal to 0. So what we need to do first is we need to look for the current first. Current to 5 Henry is very huge inductor, I can say. 5 Henry inductor when you have the Vt is equal 30 T squared when T bigger than 0. So what calculation that we need to use? We need to use a V, L, Vi over Vt. So, sorry, we need to use this calculation I, how to determine the current inside the inductor, 1 over L, T0 to T, Vt dt. So you have here then, you need to do the integration of I 1 over L using it. 1 over L T0 over T Vt dt. What is the Vt? When T to T0 to 5, kan? Kita diperlukan find the current T sampai 5 seconds. So Vt is 30 T squared just now dt, and then you do the integration of it. And then we know that the IT is equal to 0. Can somebody calculate, start calculating that? We have the L is equal 5 Henry here. This is the value of the L. So we can write down 1 over L. Kami bang 0 to T. Vt dt plus I T kita ke 0. Which is in this case, this will be a 0 as mentioned here. I ketika 0 plus 0. So there is no initial current. It's a memory effect. Now you can put down 1 over L. Kami T over 0. What is our VT? Our VT is 30T squared, right? So we 30T squared. Oh, I'm struggling to write down using my mouse here. VT. So L is 5, 30 over 5. And then this is 3 over 3 over 3. So 30 over 5, we will get times here 6 chicken lagi. So finally we will get 2T kuasa 3 ampere. So that's the equations. What the value is 2, 3 by the power of 3. So if the current until T is equal of 5, so what is the current at T is equal to 5? So the current will be 2 kali 5 kuasa 3 is the current, the value of current at 5 second. So we have here in the situation sebutan yang you boleh gunakan atau menentukan value of I. So this is how you calculate the I inside the inductor. 2T kuasa 3. Now the second part of the question is to find the energy stored between 0 to 5 seconds. So we would like to know how big the energy that can be stored from 0 to 5 within 5 seconds. So we will use the equation of W is equal half Li squared. So we know Li squared is, so we can use this way. W is a common of P dt. So where you have P is equal VI over VI, P is equal VI. So we know the VI will be T kuasa 3, right? 2T kuasa 3. So I is 2T kuasa 3. Just now kita dah kira. V is berapa tadi? Berapa V kita? 30 T kuasa 2, right? 30 T kuasa 2. So P is equal V times I, 30 T kuasa 2 kali 2 T kuasa 3, then you get 60 over T kuasa 5. So that's the power. And the energy stored is then W is kamiran P over dt. So P over dt is equal 0 to 5, because we would like to know within 5 seconds how much energy that you will store. So 60 T5 dt. So simplify, then we can get 156.25 kilojoule energy stored inside the inductor during that 5 seconds. Alternatively, we can calculate W using, here you can see what we should do is we calculate the energy at 5 seconds, and then we calculate the energy at 0 seconds, and then we try to minus W0 is equal to half L. The L is a 5 value, 5 Henry. I squared is 2 times 5 by the power of 3 to T squared, T 2 times 3, T equals 3. So this is the one that the value here. And then you change the T value 5 and 0. And then when you try to calculate, you will get 156.25 kilojoule, similar that using the technique P is equal IV. Okay. So that's how you determine the value of the energy produced current inside the inductor at the very. Please bear in mind, in capacitor and inductor, all the value, the current, and the voltage are really determined, are really different from time to time. So we need to be exact at which point that we would like to know the voltage or the current that will be produced and generate inside the circuit components. Okay, so how brief is brief? Similar to capacitor, we would like to know there is a parameter called time constant or tau. So it depends on the inductance value, inductor value, and the resistance in the circuits. Okay, so tau is equal R over L, and then from here you can see that one example that I can show you, the storage phase. Yeah, it really depends on the versus the decay phase. So this is switch connected to power supply, and the charging will happen until it's reached the maximum point, fully charged stage. So you can see here it's a fully charged stage has been achieved at 3T. And then when the switch is connected to this charge, then the current will reduce significantly and goes back to 0 at a certain period of time in which can be determined by the tau. The tau storage phase is equal to the L divided by Rs. So it really depends on also the currents and also it really depends. The tau value is dependent on the resistance and the capacitance, the inductance of the circuit. Okay, so the VL is equal, and VL and IL can be calculated in the same manner. So all these, the charging and discharging happen really fast, but it serves certain purpose inside the circuit elements. Now we can see how the inductors can be calculated when you have various or many inductors are connected. So similar to the resistors, inductor in series can be easily calculated. The total inductance can be easily calculated. LT is equal L1 plus L2. So if you can see last time, when we try to calculate a capacitance, is this opposite way when we calculating capacitance total value when compared to resistor. Here, the inductor are same or similar way when you try to calculate the total resistance or total inductance. In this case, the L1 and plus L2. When the inductor are in series, the L1 will be plus, and you get the total of it. Okay. So the parallel connection have the same technique or same possibility to how to deal with it. So here you can see the parallel connection have a similar way to calculate, as a parallel in resistance. In terms of technique, series and parallel, capacitor and inductor are one way or similar method, and resistor and inductor have the same way to calculate the total or equivalent resistance or inductance, while the capacitor have a opposite way in terms of calculating the series and parallel. So much more easier for you to memorize. Okay, so just remember how to calculate resistor and inductor are the same. So perhaps we can try for a while. In order to avoid you guys become very sleepy and a very hot afternoon here. I'm not so sure in your place. So try to determine what is the total LAB. So I give you 5 minutes to try to solve this, and then we will come back with the solutions. 250, okay. Okay, berapa jawapannya? Iqbal cakap 250. Ya, Iqbal ni. Ikut lagu, copyright. Kick W apa? POG apa? Mama muda? Tak faham aku korang ni bulan ni. Okay. So LAB is 267.84. Let's see. So let's try to solve it. And so kita selesaikan yang ini, yang series dahulu. 60 campur 40 will be 100. So 100 parallel with 26, and then this will be parallel to with the 100, and then you add up. So berapa jawapan yang ni? 100 parallel to 26. Dua boleh bagi komen. $250 example sebelum ni. Okay. So we will be 1/LT is 26 times plus 1/100 times 26 berapa? 0.048. Saya pun tak ada jawapan dia, saya kena kira. Gini kan. 126. Okay, so this will give us 20.63 Henry. So 20.63 will add in series with 50 ohms, 50 Henry here. Okay. So that will become 70.63. So that 70.63 will parallel with 100 Henry. So the LT will become 1/100 plus 1/70.63 equal to, so LT will give you 100 times 70.63 divided by 170.63. So this will give you 41.39. Okay. So this all together will give you 41.39. And this, from there, you will get the This is 25. This is 150. This is 25. This will become 41.39. Okay, so I can show you. So that 41.39 will be parallel with to here. So, jangan tunjuk kat camera je. So the circuitry will be simplified to this range where you have the 41.39 parallel with 25. Susah sikit That's why I draw it this way. So now we can simplify this 41.39. This is 200. This is 50. $150. So 25 times 41.39 divided by 25 plus 41.39. $15.59. Let's give you 50.59. So now you can see here, so you can see these two now are in series. Later I will post in the groups how I solve this so that you can, these are in series and parallel to this before it's become parallel to this. Okay, then you get 60. When you try to calculate or determine the value here between these two parallel, then you get a 62.34 Henry. simplify it once more. Sixty-two point 34 times 25 divided by 87.34. So we have 17.84. Now altogether is LAB is equal to 200 plus 17.84 plus 50 Henry. 205,667.84. So the answer will, let's see, ada tak yang jawab? Saya tak boleh. LAB is equal to 267. I will post the final calculation later on so that you can refer it to. So let's take a look at the application of this components of inductor. So due to their bulky size, inductor are less frequently used as compared to capacitor because as you can see, however, application where they are very best suited, they can use to create a large amount of current or voltage for a short period of time. So their resistance to sudden change in current can be used for spark suppressions, and then along with capacitor they can use for frequency filter. Okay, frequency filter sama seperti macam capacitor. You can use inductor also to do filtering. Okay? Using a lot in filtering. So these are the overlapping application between capacitor types. In diagram here, this is capacitor and inductors, how they can work together to improve the smoothen the value or the waveforms. Okay. So here you can see the capacitor is being used to reduce all this spark inside there. That's why it's always used as in the audio application because it can smooth out all the noises, all the noise. AV flyback also using in tuner using inductor and capacitor. So these are some of the example that we use. For power lines or low frequency circuit under 100 microhertz, under 100 megahertz, so we use for choke and resonance circuits. So RF inductor for more than 10 megahertz. For impedance matching also. And I think that's all for today for you to understand the basic and the fundamental of inductor. So any questions? Siapa lagi yang require attendance can write down your name so I can just straight away pick it up. Chat. So ada yang memerlukan lagi attendance, saya akan key in manually before we end the session. Haris Hamzan. Sebentar mana tadi? Sure. I already post the capacitor notes in the Google Classroom, so you can get it from there. So Pritam. Okay. Wait. Irfan Haziq. Okay. Awis Hamizan. Okay. Shankar Subramaniam. Muhammad Aiman Alias, eh? There is no note in Google Classroom. Ada ni. Ya. This capacitor tambah. Saya tambah untuk hari ni punya. Oh, saya belum post. Sorry. Okay, I will add on all the notes of this. Thank you very much. Kalau ada question, you can continue inside the notes, inside the ni. Okay.